Let us consider two non-empty sets A and B. So set A contains the elements A, B and C, while set B contains the elements 1, 2 and 3. So we're going to find out the Cartesian product of A and B, and that should give 9 ordered pairs. So we take the element of set A and then form an ordered pair with each of the elements 1, 2 and 3. So that gives us A1, A2 and A3. Then we pick up the second element, which is B, from set A, and then form an ordered pair with each of the elements of B, and that should give us B1, this is B2, and we have B3. And finally we pick up the last element from set A, which is C, and then form 3 ordered pairs with each of the elements of set B. So now that we have the Cartesian product of A and B, what we're going to do, we are going to define a relation. Let us call the relation, instead of calling it representing it by R, we are representing it by F. So we have a relation F, and we are going to pick up some special elements from this particular Cartesian product. So let me pick them one by one. So we're picking from here A1, then we pick B2, and then we pick C3. So we can also represent this particular relation F using the graphical method. So we're going to draw two Venn diagrams, each containing set A and set B, and then we are going to use an arrow diagram to map the values from set A to set B. So we have the relation F going from A to B. So we consider the first element, which is A, and then map it to the element 1 in set B using an arrow diagram. Then we consider the second element, which is B in set A, and then we map it to element 2 in set B using an arrow diagram. And finally we pick up the element C in set A and map it to element 3 in set B. So this is the relation going from A to B, where the elements in A, B and C are mapped to some elements in the set B. Now here we can clearly conclude a few things from this particular relation. The first conclusion that we can draw is that our relation F is a subset of the Cartesian product of A and B. Secondly, we also see that each of the elements in the set A has got a unique image in B. So each elements in set A has a unique image in our set B. Third conclusion that we can draw out is that all the elements in set A has been used up, meaning whenever we pick up each of the element in set A, so it is going to give us its corresponding ordinate value in set B. So these are the three conclusions then we can draw out from the given relation F. So now that we have, these are some unique relations, so unique conclusions that we are drawing out from this particular function F. So now we are ready to formally understand the definition of a function. So here in this question we have a set A having 4 elements, 1, 2, 3 and 4, and we are given a set denoted by F, which is a subset of the Cartesian product of A and A, and this set F is defined by the set of all ordered pairs x and y such that when we add x and y, their sum must be greater than 4, and those elements x and y belongs to a set A. So let us try to find the ordered pairs that is going to satisfy the given condition that x plus y is greater than 4. So we have f. F is a subset of A cross A. So we have f, which is defined as a subset of A cross A. That means f is a relation going from A to A. Now let us first find out the first ordered pair. So we're going to take the element 1 from set A. So let x equals to 1 is the first element that we are picking up from set A. So the corresponding y value will be y is equals to the sum must be greater than 4. So we have to pick a value such that when it's added to x equals to 1, we get a number which is greater than 4. So that number can be only 4, because we know 1 plus 4 is going to give us 5, and that number is going to be greater than 4. So we form an ordered pair 1, 4. So this must belongs to our set F. For any other combination, we will not get an ordered pair which satisfies the condition as given by the set F. So we have the first ordered pair. So we have 1 going to 4. So we represent it by an arrow diagram going from the first set A to the second set A, to its corresponding element in the second set A. Now we're going to consider the next element from set A. So we have x equals to 2, which belongs to set A, and the corresponding y value must be such that when added to x equals to 2, we get a sum that is greater than 4. So the only possible values are 3 and 4. So we have the ordered pair 2 and 3 belonging to our set F, and we have the next ordered pair, which is 2 and 4, that belongs to our set F. When we come to the third element picked up from set A, so we have x equals to 3, which belongs to our set A. Then we can pick up either a y equals to 2, y equals to 3, y equals to 4, and the corresponding ordered pair will be 3, 2, 3, 3, and 3, 4. Now each of the ordered pairs are going to belong to our set F. And finally we pick up the fourth element, which is 4, from set A, and the corresponding y value will be y equals to 1. So that will give us the ordered pair 4, 1, which belongs to set F. We'll have y equals to 2, and that will give us the ordered pair 4, 2 belonging to our set F. We can also pick up y equals to 3 because it's going to satisfy the condition that the sum is going to be greater than 4. So we have 4 and 3 belonging to our set F, and the final value of y4, so that will give us 4, 4 belonging to our set F. So we can complete this graphical representation. So we have 2 mapped to 3 and 4. So we'll draw an arrow going from the first set A to the second set A, and we'll map it the corresponding elements. So 2 goes to 2, 2 goes to 3, and 2 goes to 4. Then from 3, from the first set, it is mapped to the elements 2, 3, and 4 in the second set. And finally we have the element 4 in the first set A. It is mapped to each of the elements of set A, the second set A. Now that we have determined the relation between the two sets, what we have to check whether this given relation is a function or not. So let's look at the first criterion. The first criterion states it could be in any order. So I'm considering this as the first criterion, that each of the elements in the first set A must be used up. So we see that each of the elements of the first set, which are 1, 2, and 3, 4, 1, 2, 3, and 4, they are getting used up. So they are being mapped to some elements in the second set A. So this satisfies the first criterion. Let's go to the second criterion. The second criterion states that each of the elements in our first set A must have a unique element in the second set A. So here, okay, it's fine that one has a unique element. So one has a unique element in our set, the second set A, which is 4. Now that's fine. That belongs to our set F. However, although we have 2 uniquely mapped to 3, but we also have 2 mapped to, which is mapped to the element 4. So that means we have the element 2 in the first set A, which are giving us 2 images in the second set A. So we have 2 images. So this means that 2 is not uniquely mapped. So 2 is not uniquely mapped. So this means that our given value f, our given set f, is actually a relation. It is not a function. So here we have a set A containing the elements 1, 2, 3 and 4, and we are given another set F, which is a subset of the Cartesian product of A with itself, and this set F is defined as a set of all ordered pairs x and y such that y is equals to x plus 1. So let us try to form the ordered pairs, which is going to satisfy this equation y equals to x plus 1. So we pick up the first element from the first set A. So for x equals to 1, which belongs to our first set A, the corresponding y value will be equals to 1 plus 1, which is equals to 2. And we see that the element 2 belongs to our first set A. So that means we have a valid ordered pair, and that is going to belong to the set F. So we see that 1, the element 1 from the first set A is uniquely mapped to the element 2 in the second set A. Now we go to the second element in our first set A. So for x equals to 2, so we have this element belonging to our first set A. The corresponding y value will be equals to 2 plus 1, which is giving us 3, and we see that this element 3 also belongs to our set A. So that means this is also going to form a valid ordered pair, and valid ordered pair in the sense that this is going to belong to our set F. So here we have, when we pick up the element 2 from the first set A, this is uniquely mapped to the element 3 in the second set. Now we go for the third element. For x equals to 3 belonging to set A, the corresponding y value is equals to 3 plus 1, which is equals to 4, and this belongs to our set A. So the ordered pair 3, 4 is going to belong to our set F. So 3 is uniquely mapped to the element 4. Now we go for the fourth element. So x equals to 4 belonging to our set A gives us the corresponding value of y, which is 4 plus 1 equals to 5. But the element 5 does not belong to our set A. So that means the ordered pair 4, 5 does not belong to the set F. Now here we have a problem. The problem here is that the element 4 has got no image in a second set A. So this is now no corresponding image in our second set A. So that means it has not been used up. So that means our given set F is actually not a function, but it is only a relation going from the set A to this itself. So we'll say that F is not a function defined on A going to A. However, F is a relation. So in this question, we have a new set F, which is a subset of the Cartesian product of A and F. And this new set F is defined as the set of all ordered pairs X and Y such that the sum of X and Y is equals to 5. It's given that X and Y belongs to our elements belonging to a set A. So let us try to form the ordered pair. So we'll pick up the first element. So for X equals to 1, we have to pick up a unique element Y from set A itself such that their sum is equals to 5. So we have this, we can rewrite this equation as Y equals to 5 minus X. So for X equals to 1, so that gives us the corresponding value of Y, which is 4. So that means 1 and 4, the sum is going to be equals to 5, and this belongs to a set F. So here we can say that 1 is uniquely mapped to the element 4 in second set A. Now we pick up the next value of our X. So for X equals to 2, so we have a corresponding Y value as 5 minus 2, which is equals to 3. Now the ordered pair 2 and 3 is going to be valid because the sum is exactly equals to 5, so it is going to belong to a set F. So here we can say that 2 is uniquely mapped to the element 3 in the second set A. And then we pick up the third element, which is X equals to 3 from our set A, such that the corresponding Y value that needs to be picked up is going to be equals to 2. So 3, 2 is going to be the ordered pair, and this is going to belong to a set F because it satisfies the condition that when we add 3 and 2, we are getting exactly 5. So we have the element 3, which is uniquely mapped to the element 2 in a second set A. And let's pick up the final value of X. For X equals to 4, so we have the corresponding Y value 5 minus 4 given by 5 minus 4, and this value is equals to 1. So we see that the ordered pair 4, 1 is going to be valid ordered pair, and it is going to belong to a set F. So here we have the element 4 in the first set A uniquely mapped to the element 1 in the second set. Now it was given in the question that F is a subset of A cross A. In other way, that F is a relation going from set A to set A. Now we see that each of the elements of the first set A has been used up, so that means all the elements must be exhausted. So it satisfies the first criterion of being a function. Then we move on to the second criterion. Each element, or you can say every element in the first set, that is A, is uniquely mapped to an element in the second set A, meaning each element in A has a unique image in the second set A. So since it's satisfying both the criterions of being a function, we can safely say that our given set F, so we can say that set F is a function going from A to